Here's a really standard sample final exam stats 1 question. How large or small does an observed mean based upon a random sample of 12 observations have to be significantly different from 3.1 at the 5% significance level, assuming normality and a population standard deviation of 2.4. Now, these might seem like a lot of words, but all these words can be put into the standard hypothesis testing symbols. And that's what I want you to do. I want you to pause this video and see if you can put this word problem into the standard hypothesis testing symbols. And then I'll show you exactly, step by step, how to get the right answer on this question, and maybe even pick up a little partial credit if you're not fully comfortable with all the algebra. So pause the video now. So let's put this into statistical symbols. So when you see significantly different from 3.1, this actually tells you your alternative hypothesis. Now, some professors will use H1, other professors will use HA. It doesn't matter. Use whichever one your professor uses. But the alternative hypothesis is that the population mean is going to be not equal to, that means different from 3.1. So you do your alternative hypothesis first, and I've left a little space for the null hypothesis, which says that the population mean is equal to 3.1. And just to remind you, this is the Greek letter mu. It's a letter in the Greek alphabet. It's pronounced mu like mucus, not moo like the cow. So we have the null hypotheses. The next thing we have is that alpha equals 5%, and we have that the standard deviation is equal to 2.4. Now notice I used the lowercase Greek letter sigma for the standard deviation because this is a population standard deviation. So because it's a population standard deviation, you use the Greek letter sigma and you use the Greek letter alpha for the significance level of the test. So it already says we have a random sample, and the 12 observations, that tells us that n equals 12. So we're almost ready to begin. And there's a little construction that will help you visualize this perfectly. So I'm going to motivate the construction. And to motivate the construction, I want to give you a little shortcut. When you're dealing with a two-tailed hypothesis test, where the alternative hypothesis has a not equal to, it's very often the easiest way to go, not the only way to go, but the easiest way to go is to really focus on where you fail to reject the null hypothesis first. And so here's where a nice little construction comes in. So I'm going to draw a picture of the standard normal distribution, and we use the letter Z to represent the standard normal distribution. Now, if we have a two-tailed hypothesis test, that means our 5% of the type 1 error is shared on both tails of the standard normal distribution. So since this is 5%, 5 divided by 2, which is a half of 5, is 2.5%. So we have 2.5% on either side. And I like to shade this in because even if you screw up some of the algebra, this will speak to your professor. Now this region here, if you can draw this diagram, this is going to speak to your professor. This region over here is where we fail. I'm going to write FTR, fail to reject the null hypothesis. So I'm going to put little arrows here. So this little area here is where you fail to reject the null hypothesis. This tells us to fail to reject the null hypothesis when, now watch this carefully, our z-score that we observe is between, now this is negative z sub alpha over 2, and this is positive z sub alpha over 2. Now I have a whole video on z sub alpha notation, but this is the Greek letter alpha, this here, and this is the Hindu Arabic number 2. So in almost any statistics textbook that I've ever seen, you have a z sub alpha table, and it should look something like this table over here. And z sub alpha, this is z sub alpha, but we want z sub alpha over 2. And so if alpha is equal to 5%, then alpha divided by 2 is 2.5%. So that means we're going to have to look up 2.5% in our table. But this isn't in percentages, this is in decimal. So 2.5% converted to a decimal, you would move the decimal point 2 places to the left. And this gives us 0.025. So this is a half of 5% in decimal. And it tells us that our z sub alpha is 1.960. Now I'm not going to bother putting in the 0, I'm just going to write 1.96. So here we have negative 1.96. And here we have positive 1.96. And these are called critical values. And even if this algebraic part that I'm going to show you now is a little difficult, if you have a professor who gives you partial credit, write the word critical values. You know, you'll pick up some partial credit. You'll impress the professor that you know that these are critical values. Now, if you don't have this kind of a table, if you have a percentile table, this is the 2.5th percentile, negative 1.96. And because the normal distribution is symmetric, about 0 if it's a standard normal distribution, then this is the 97.5th percentile. Why? Because 100 minus 2.5 is 97.5. But most likely, you'll have a table similar to this table in your textbook. So hopefully, you won't have to look at a percentile table, but you might. So that tells us that we want to fail to reject this null hypothesis when z is between negative z sub alpha over 2 and positive z sub alpha over 2. And you might not realize it yet, but this is an inequality that can be solved for x bar. Let me show you the next step, but you got to reflect on this a little bit. This comes right from the picture. All right, so this region here between negative z sub alpha over 2, which is negative 1.96, and positive z sub alpha over 2, which is positive 1.96, we are going to fail to reject the null hypothesis. This picture is the geometric representation of this little piece of algebraic notation. but I have to show you where you're going to go next. So I'll ask you, what do you think you're going to do next? Pause the video and see if you can figure out the next step. Okay, here's the next step. We have a formula for the z-score when we are standardizing a sample mean. This is x bar minus the hypothesized mean, which I'm going to call mu naught, even though we know that the hypothesized mean is 3.1. I don't want to put the number in. I want to just put the symbol in. And we always divide this by the standard error of the mean. This is the standard deviation of this x bar. So this is what the z is, right? Now, let me write down the whole inequality just so you see this. So this is z sub alpha over 2. I know the alpha looks a little bit like a 2. And this is negative z sub alpha over 2. And I want to just make it clear that this is an alpha and this is a 2. And same on this side also, right? Z sub alpha over 2. Greek letter into Arabic letter. All right, now this may seem like it's getting a little complicated, but it isn't. So the next step we're going to do is we are going to solve for x bar. That's what we're going to do. Now, why do we do that? What does it say? It says how large or small does an observed mean? So remember, x bar, the sample mean, is the observed mean. It's not the population mean, right? We're observing a sample mean. So observed mean and sample mean, synonymous terms. All right, so we have a simple inequality to solve, and I'm going to solve it on a separate piece of paper just so I can write nice and large. So we have z is between negative z sub alpha over 2 and positive z sub alpha over 2. And this is where we fail to reject the null hypothesis. And we already put in the fact that this z is x bar minus mu naught over sigma sub x bar. And we have negative z sub alpha over 2. And we have positive z sub alpha over 2. And what we want to solve is for this x bar over here. So how are we, and don't forget, this is when we fail to reject the null. So how are we going to do this? Well, I'll give you a little hint. First thing you're going to do is put parentheses over here. And then you're going to pause the video and see if you can figure out what the first step in solving for x bar is. Now, if you said we're going to multiply all members of this inequality by sigma sub x bar, that is the standard error of the mean, so that we can cancel out this denominator, well, if you said that, you'd be right on the money. So let's put it in. We have sigma sub x bar times negative z sub alpha over 2. Now I put the negative over here, nothing wrong with that. Multiplication is commutative. I hope you finished my sentence. All right, so now we have an x bar over here minus mu naught. We're closer to solving for this. And here we have the standard error of the mean times z sub alpha over 2. I want you to write this down. I want you to reflect on it. We're getting closer. Again, what are we solving for? This. Now, what I would love you to do is pause the video and see if you could do the next step. Yeah. All right. So the next step, if you said for the next step you're going to add mu naught to each member of this inequality to get x bar alone, well, you would be right. So that's what we're going to do. We're going to add mu naught, the hypothesized mean, to each member of the inequality. Right? So that's what we did. We just added this. And what we get here, right, when we add mu naught to each member of this inequality, right, this mu naught cancels out with this mu naught because this is minus, this is plus. And what we get is, let me move this up just a tiny bit if I can. What we get is mu naught minus the standard error of the mean times z sub alpha over 2 is less than x bar, which is less than mu naught plus sigma sub x bar, also known as the standard error of the mean, z sub alpha over 2. And again, this tells us where to fail to reject the null. So now, guess what we can do? We can plug in all the numbers in one shot. Take a look. Mu naught, the hypothesized mean, is 3.1. Let's plug it in. 3.1 minus sigma sub x bar, well, the standard deviation is 2.4, and the standard error of the mean, sigma sub x bar, is always sigma divided by the square root of n. But what is n? 12, right? Now I'm going to write that down for you. So sigma sub x bar is always equal to sigma over the square root of n. This is called the standard error of the mean. And that's what we're going to use. So we have 3.1 minus, now the standard deviation is 2.4. So we have 2.4 divided by the square root of, now what is n? N is equal to 12. And the z sub alpha over 2 we showed was equal to 1.96. Right. So we're just going to put it in. 1.96. This is a 6. And here we have x bar. And here we have 3.1 plus 2.4. divided by root 12 times z sub alpha over 2 we already discovered was 1.96. So I put it all in one shot just to make my life really easy. And now I'm going to grab my calculator. So the first thing we're going to do is we're going to hit 3.1 and then the minus button. And then 2.4, and then the divided by button, and then the square root button, and then 12, and then the times button, and then 1.96, which was z sub alpha over 2. And then we're going to hit the equals button, and we're going to get, let's round this off to the nearest, let's say thousandth, so 1.742. Now, here's the beautiful thing with this calculator. I'm going to take this little button here, and I'm going to scroll back, and And because of the beautiful symmetry of the standard normal distribution, all I have to do is change this minus button right here. All I have to do is change it into a plus button. See, 3.1 minus this whole business. Here we have 3.1 plus this whole business. So all we have to do is change the minus button into a plus button, and then they hit the equals button, and we get 4.45 around the 7 up to an 8. So 4.458. Now, at this point, my students always say, well, what's the answer? What's the answer? So now I'm going to give you the answer. The answer is her observed mean. I'll write out observed. Her observed mean is significantly, I'm just going to write SIG period for significantly, and I'm going to write DIFF for different, from, now what was the hypothesized mean? 3.1. See, that's what it says, significantly different from 3.1. So you write 3.1 at, now instead of the 5% significance level, I'm just going to write alpha equals 5% so I can fit it in. But that's the same thing as the 5% significance level. When her observed mean is either less than 1.742 or greater than 4.458. And that's like a full credit written down answer to show your professor that you fully understand this. Now, that's because significant, the word significant or statistically significant means that we reject the null hypothesis. That's what significant means. This whole series of calculations were based on failing to reject the null hypothesis. But I did it this way because it was mathematically just the easiest way to roll through this. So full credit answer, her observed mean is significantly different from 3.1, the hypothesized mean, when her observed mean, the same as the sample mean, is either less than 1.742 or greater than 4.458. And that's the full credit answer. I hope this was helpful, and if it was, like and subscribe.